in collaboration with Liverpool Football Club. Petar is staff research scientist at Google DeepMind, affiliated lecturer at University of Cambridge, where he obtained his PhD as well. He's recognized for his works in graph attention networks and deep graph informatics. Petar, the stage is yours.
All right. Thank you very much, Łukasz, for the fine introduction, and thank you to all who are tuning in for my talk today. As mentioned, my name is Petar Veličković, staff research scientist at DeepMind and affiliate lecturer at the University of Cambridge. And for today's session, we'll be talking about designing an AI assistant for football tactics, which was a pretty exciting and, I must say, really fun collaboration that I've had a chance to participate in over the past couple of years. And finally, we're starting to see some concrete products out of it, which I'm very pleased about. So let's dive headfirst into the topic. When we say AI for sports, what do we really mean? It might appear to be somewhat obvious, but I feel like it is useful to try to put some concrete pointers on what we mean by this term. So in sports, and specifically we're thinking of football in this particular application, you have in the real world sport coaches whose many jobs include various forms of tactical analysis of their team, as well as competing teams, and figuring out both the best tactics and the best counter tactics in response to what opposing teams come up with. So what do we mean by an AI tactical assistant? Well, generally, in order to come up with good tactics and counter tactics, you need to be able to detect interesting, salient, actionable patterns in the football game. And the specific way in which you come up with these patterns can be quite tricky, especially for human observers if you have to process large quantities of data, especially in a highly dynamic environment like football is. So an AI tactical assistant might be imagined as any kind of system that is able to help human coaches make more sense of the world of football through very careful analyses of various kinds of data, such as tracking data, video data, audio data, or textual data summarizing various matches, and trying to see what are the important salient features from which we can then come up with the more elaborate tactics in the future. And it might also be interesting to ponder this question from the opposite direction, like why would it be good for us to, like, it's clear why the use of AI might be helpful in sports analytics. There's a huge dynamic stream of data from a highly noisy and challenging environment, and basically artificial intelligence, one of the main selling points of artificial intelligence is that it can help us make sense of large quantities of data like that. But I feel like it's also useful to study this question in the opposite direction. Like, why is sports an interesting domain for artificial intelligence? And in my personal opinion, there are three pretty interesting points for why AI for sports and sports coaching specifically is something that is quite interesting. First of all, it gives us a nice, safe, and controllable test bed for AI research, because we are required by the nature of the environment to produce interpretable representations, processing potentially a multimodal stream of data, and we need to make decisions that are applicable in a real-world multi-agent system. And it's very rare to find a nice concoction of these three properties so clearly lined up side by side. And maybe it should come as no surprise that then sports is a very interesting melting pot of various disciplines of research, like computer vision, game theory, statistical learning, and so on. And also, in many cases, you can define very clear metrics that you can use to measure the progress of your methods and track success of your methods. So there's many things about sports as a domain which can be quite favorable for artificial intelligence research, generally speaking. So along with many collaborators at Google DeepMind, we have set on a journey to try to exploit artificial intelligence methods over sports data as much as we could. And our journey really starts around 2019 and so on, and 2020, when we also made our first visit to our collaborators at Liverpool, that you can see in this picture over here. And one of the one of the key publications which came out during this period was the game plan paper, authored by Carl Toils and others, published at JR, where this AVAC, or Automated Video Assistant Coach, concept is proposed. Now, what do we mean by the AVAC? Generally speaking, you might be interested in answering complex questions about a football match. For example, you have a camera which shows you the state of a match at any particular point in time. And you might be asking yourself then, okay, what has happened off screen? Like, what is happening in this game that the camera is not showing? And this is actually a really complex question to answer, which might rely on a lot of different aspects of machine learning research. For example, we might need some aspects of quality representation learning to be able to learn a system like this over large quantities of multimodal data without necessarily any structure attached to it. Then we might need to incorporate some explicit aspects of predictive and generative modeling to be able to reason about what happens away from the field of view of the camera. And lastly, in order to make interpretable and useful profiles coming out of these kinds of systems, we might also be interested in game theoretic research on human factors that allows us to more explicitly model the specific traits of individual players. So really, what goes on when a system has to answer a question like what happened off screen? There are a lot of very important aspects that might fall into a system that answers these kinds of questions. And the game plan paper is one very nice overview paper that outlines the kinds of things that need to go into a system like this. Building up on the initial results outlined in game plan that motivated this research direction, in 2021, there have been several very important external outlets where we have cemented our claim to applications of AI for sports and our commitment to further research in this area. Basically, first, within one of the popular artificial intelligence conferences, IGCAI 2021, we had organized a workshop on AI for sports. Then Carl Toils, and along with two co-authors, has co-published a book on AI for sports, which is also a really interesting and useful reference if you want to learn more about it. And for those who prefer podcasts, AI for Sports also featured in the second season of DeepMind, the podcast with Hannah Fry, which is another kind of very popular outlet where we showcased various aspects of our AI for Sports research. And this leads us to 2022, where moving from some of the primary concepts outlined in the game plan, we have actually been able to publish a paper in Nature Scientific Reports called the Graphimputer, which effectively is one of the first kind of self-contained modules that embed the kinds of predictive tasks that a human coach might find particularly useful. And this was a result of a very continued and onward collaboration with Liverpool, and which also led to our second visit to Liverpool. And this was also around the time when I have joined the project. So you can see me in the center of this picture at Liverpool's training grounds. And we won't talk in a lot of depth about the Graphimputer here, but one thing that is important to note about the Graphimputer is that it tries from abstractified tracking data to answer this question of what is happening off camera. So here you can see the trajectories of various players in a football game, but a camera, which is showing you the live action in a football game, does not show you where all the players are. Rather, you can only see the action of some of the players which are near the ball. And this is problematic if you want to, say, analyze how well is one particular player behaving. For example, in a scouting scenario, if you want to detect potential future players to acquire for your team, you might normally be sending scouts out to watch the game live and track players live, but this is a potentially costly process. So it might be really, really useful if you could have a system that is capable of just watching the video recording of a football match and based on that figuring out how all the players are behaving. But this naturally draws with it a complicated problem of figuring out where are all the players that are not on the camera right now moving. And this is what the graph imputer set out to do, using a combination of graph machine learning, supervised learning, and inspiration from game theory. Graph imputer is capable of basically generating probable sequences of where each player is moving, regardless of whether or not they are currently on camera or off camera. And systems like these can perhaps be an important way to automate some of the tasks that humans might not be able to do manually. So the successes of graph imputer have set us on a trajectory that leads us to this year. And in this year, we have actually set out to build a complete system that might be able to serve suggestions to human coaches. And to build a useful kind of fully packaged system, we need to be able to answer several categories of questions, which are closely intertwined with one another, as we will see later in this talk. So we might need to have a system that's capable of answering questions like, what will happen in a particular football situation? This leads us to predictive modeling. You might be able to need to answer the kinds of question of, okay, provided something happened, can you analyze what actually happened? So in this case, predict some embeddings from your situations and use them to support various forms of retrieval so you can mine similar situations. And maybe one of the most interesting problems in this scenario is what could have happened if I wanted to optimize for a particular outcome. And this is the guided generation objective. And satisfying these three kinds of questions, like being able to answer them more efficiently, is what led us to develop Tactic AI, an AI assistant for football tactics, which is joint work from Joe Long, myself, Daniel Hennis, and many other great collaborators from both DeepMind and Liverpool Football Club. So in the remainder of this talk, I'll be telling you about Tactic AI and how we've been able to build it using the various components that you see outlined on this slide over here. So I need to, before we dive into Tactic AI, I feel like it's useful to mention how these three works that Google DeepMind and Liverpool worked on together over the years kind of gradually ascend the ladder of automated tactics assistance. So Game Plan is really a paper that answers the why, like gives some motivating examples for how AI works, while only like presenting a relatively isolated qualitative study. Specifically, Game Plan looked at penalty kicks to show that some forms of statistical analysis can be quite useful there. Then Graph Imputer took this a step further and tried to directly answer a question of, okay, we have an idea, we have a feeling that AI could be useful to assist football tactics. Now let's try to answer the question of how can AI be used to analyze football tactics. So Graph Imputer, specifically looking at the question of where are the players moving off camera, provides a concrete prototype of a system that can automate a task that is really challenging for humans. And lastly, Tactic AI is really trying to give the what. So what is an example of a practical AI football tactics assistant? So what Tactic AI does is it doesn't just focus on one task or motivating a particular task. It really aims to provide a full system that's capable of providing useful suggestions to a human coach. And specifically to make this claim a reality, in our work, we focus on corner kicks as a test bed. Now, I feel like it is important to try to motivate why do we specifically focus on corner kicks here. And maybe let's take a step back first and think about the specifics of having to do predictive or generative modeling inside the game of football. As you might imagine, football is a highly dynamic sport that's really hard to influence. Like, even if you had a really powerful system that was capable in real time to tell you what aspects of tactics are working out or not working out, it would be really tricky to make changes to these tactics in real time. And even if you were able to do it, you might end up confusing the players because they need to keep their minds focused on the game that's taking place in real time, right? So making any real on-the-fly suggestions is actually quite tricky in open football play. So that's not as easy of a domain to deploy, packaged products that make useful suggestions. However, fortunately for us, there exist many moments in the football match known as set pieces, such as this Liverpool corner kick that you can see here. And during a corner kick, the game state is effectively frozen because the ball is placed in the corner, the different players are orienting themselves, and the corner taker then drives the action that will happen afterwards. So this now is a setting where the game is not moving as dynamically as it would in full open play, and there might be ways in which we can make suggestions that are actually influential. And by the way, some of you have probably seen the movie Moneyball, which if you haven't, I recommend taking a look at it. It's another good example of using statistical methods in improving sports analytics. One of the reasons why Moneyball was so effective in the game of baseball is because, in some sense, in baseball, every single game step is a set piece, right? Every single action step in baseball, all the players are frozen in place, and a new a new situation arises where you can come up with new kinds of statistics that you can decide on how to distribute your players, which players to acquire, and so on and so forth. Okay. And so assuming that set pieces are a relevant place where we can influence our analysis, there are four main types of set pieces in football: penalties, throw-ins, free kicks, and corner kicks. Penalties also make a very interesting setting to study here, and in fact, the game plan paper already studies penalties in more detail. But out of these four, really, corner kicks are the ideal candidate. Why so? Because first of all, they're frequent. Every single football game has a quite sizable number of corner kicks on average. They are quite rigid. They always take place from the same situation. That is, the ball is always in the corner. Whereas with free kicks, you depend on where exactly a foul has taken place in order to, decide from which position you're taking the free kick. And also, in every situation, a corner kick will give you an opportunity to immediately score a goal, right? Corners are really the only set piece in football that give you these three properties at the same time. And maybe it should come as no surprise then that the strategies for corners to allow for them to be executed in the most smooth possible way are often decided up front before a game even takes place. So if you have a good corner kick analysis system, you can definitely use this to actionably influence how a particular game might unfold. So accordingly, to make Tactic AI an actually immediately useful system, we make it a corner kick analysis system. Now, once we have decided we want to focus on studying corner kick situations, let's talk a little bit about how we can build a machine learning model to deal with those situations. And specifically in Tactic AI, we are focused on understanding the different relations between the players, and perhaps in the setting of corners, this becomes all the more important because various player synergies can be significantly exploited when designing tactics and counter tactics in corners. And one very nice data structure to model implicit relations between objects are graphs. So accordingly, we focus on graph neural networks as a system, as a machine learning model that can process these kinds of situations. Now, specifically, what do I mean by this? So whenever I show you a corner situation like this, well, here with only 6 players, but just to make the illustration more clear, what the machine learning model actually sees is tracking data of each one of these individual players, and we represent them as nodes in a graph, where each node and each edge in the graph has a certain feature vector associated with properties of that player and any properties between pairs of players that we're aware of, such as are they on the same team or not. And then this particular graph structure with node features corresponding to player vectors and edge features corresponding to player synergies or equal or not equal teams can then be sent across to a graph machine learning method, which usually will employ some form of message passing. Message passing, in a nutshell, is just an operation that updates the representations of each player starting from these input vectors x into some latent space vector h in a way that directly depends on the representations of all of the neighboring nodes, or in this particular case, if we use a fully connected graph, all of the other nodes. And the features of the neighboring nodes and the features of the corresponding edges will drive the specific messages that are being sent across this graph. And based on the aggregation of those messages, you will compute updated features for each player. Now, this is a very neat analogy because you can very nicely stick various kinds of features at various granularities in this graph. So as we already mentioned, in node features, you can put various player properties like their playing positions, velocities, heights, weights, and their ball possession during the game. In the edge features, you can, for example, put a binary flag telling you, are these two players on the same team or not? And you can even put features that are global on the level of the entire graph, such as where are the home and away goalpost positions, what's the time of day, what's the weather conditions, and these kinds of things. What's the current score? And this then also allows you to easily specify a plethora of various predictive tasks. So you can predict whether or not a shot has taken place in this corner as graph classification. You can try to predict which player will receive the ball after the corner as a node classification. And you can try to predict positions and velocities of various players also as node regression. And we did not actually stop at graph machine learning because this was a great way to process data corresponding to a collection of player nodes. But another problem that we had to deal with is the fact that in real-world football games, there's not really that many games taking place every season. So there's not a lot of data that you can use to train a system like this, especially if you are focusing mainly on corners. So we had to exploit a methodology that allows us to explicitly encode some useful symmetries of the football pitch to help to hopefully reduce the solution space that our neural network is searching for. So what this means is that if we have a input corner situation like this, what we can then do is generate all the different variants of this situation where we would expect the answer to be exactly the same. So specifically, one such transformation that we employ heavily in our work are horizontal and vertical reflections, right? So this is a very nice symmetry of the football pitch. If I were to reflect my football pitch either horizontally or vertically, it is, for all intents and purposes, can be considered the same situation. And as a result, my model should ideally give me the same answers in these four situations. So what we do is we generate all four of these transformed situations. Then we feed them through Tactic AI's central model. As we discussed before, each one of these blue arrows is effectively a graph neural network with message passing over each of the four situations that we discussed in the middle. And once a joint representation over these four views is computed, you can then answer various questions about this corner kick situation, like who makes first contact with the ball, which, as we said, would be a node classification problem. Will a shot be taken or not, which, as we said, is a graph classification problem. And we can also compute interesting adjustments, which is the guided generation. So can we figure out adjusted positions of the players to increase or decrease shot probability? And if you exploit geometric deep learning in this way, it can be highly beneficial for data efficiency because now your model does not have to relearn that these four reflections should be processed identically. Your model is mathematically forcing the model to behave in this way. And this is very useful because in football, unlike most deep learning applications, we don't really have a lot of gold standard data with only about 100 games played every season. And the way we use the geometric deep learning blueprint will depend on the way in which your symmetries manifest. If your tasks are invariant, like receiver or shot prediction, right? So the identity of the receiver or whether or not the shot happened doesn't change with the reflection, then you can predict based on the average of all the 4 frames you've generated. But sometimes your tasks might be what is known as equivariant, like if you want to predict adjusted player positions, if you have reflected the pitch, then the predicted positions should also be reflected. They don't stay the same. So in these situations, we don't predict based on the average of all frames, but we predict based on the identity frames view. And you can then kind of put all of these predictions together and look at, for example, guided generations, which is one of the outputs Tactic AI can provide for you. So to see what guided generations can do, let's consider this particular corner here. In this particular corner, a shot has happened for the attacking team in red. And I've highlighted a few specific parts of the situation so you can see, so you can focus on them when I show you an adjustment proposed by Tactic AI. So Tactic AI is then capable of predicting updated positions and velocities for the defending players, such that the probability of a shot, as predicted by its shot prediction model, is reduced. And in this particular case, I specifically draw your attention to these 3 red and yellow circles. The players that are relevant for these 3 circles are now positioned better, and they make more active, more intercepting movement to block the 3 corresponding attackers, 2, 3, and 4. And these changes do not only have an effect on reducing shot probability, they also affect the Tactic AI receiver predictor. Specifically, previously, you might have had a higher receiving probability for attackers 2, 3, and 4, which are in the box. Actually, making these adjustments to the defensive players now drastically increases the probability that attacker 1, which is far away in the back, will receive the ball, which further emphasizes that under this positioning of the defense, the red team might not have as much success as before in sending the ball into the box. So the attacking team is now less likely to do this successfully. Now, we've built a system like this, right? It can predict the receivers, it can predict shot events, and it can predict these guided generations such that they increase or decrease shot probability. I will have to start by giving you the quantitative numbers of how well it can do those 3 things as using a machine learning evaluation, but very quickly I will show you why I don't think we should focus too much on these numbers. So in terms of receiver prediction, the best model that we've been able to build has about 78% top 3 accuracy. So if you take the top 3 predictions for the receiver of the corner that are given by Tactic AI, in about 78% of the cases, the correct ground truth receiver will be in those top 3 suggestions. On shot prediction, we have been able to achieve an F1 score of 0.64, which is not a particularly strong predictive power, but is definitely stronger than chance. And when we use guided generation, we can significantly adjust the defending team to reduce the predicted shot probabilities in situations where shots have happened. And note here, so we reduce the average shot probability in various situations from 75% to 69%. And this change is very statistically significant with a p-value less than 0.001. Similarly, we can use Tactic AI to adjust attacking team positions to increase the shot probability for corners where shots did not happen, ergo increasing the shot probability from 18% to 31%, once again with high statistical significance. And lastly, because it's not just enough to put your players in a different position to increase or decrease shot probability, if you do this in a way that produces a highly unrealistic corner, such that it's quite obvious that the attacker or the defending players would not do this without the response, we checked whether you can actually distinguish the corners generated by Tactic AI from real corners that happened. And to do this, we trained a simple MLP classifier to check whether a corner is real or adjusted. and the F1 score of this classifier was about 0.5, which is basically random chance accuracy. So at least you cannot train a machine learning model to tell apart tactic AI corners versus real corners. Now, I do not think that you should dwell too much on these numbers. I feel like they're important just from a perspective of machine learning analysis. But recall what we're trying to build here. We're trying to build a system that's actually useful for human experts. So while quantitative metrics are useful if you want to publish a machine learning paper, they don't always really indicate how easily can a human make advantage of such a system. And in the context of football, predictive power might not tell you that much, because whether or not a pass or a shot will happen may well depend on a lot of things that our model just doesn't see. For example, human psychology, how are the individual players feeling, how stressed they are, what are the weather conditions, how tired the players are, and so on, right? There are many things that we do not put in the features of our models that might very well impact which player is the most likely receiver, or whether or not a shot will take place. That, I would argue, you cannot really achieve 100% or close to 100% accuracy on these tasks. So I don't think this is the right metric to optimize for. So we wanted to really tackle this problem head on, and let's evaluate how useful such a system's output is to humans. So we organized a human case study with 5 expert raters from Liverpool, and these 5 raters included coaching assistants, video analysts, and data scientists. And over the course of the study, we showed them over 300 examples of corner kicks, asking them various questions over them. And these corners were both real and tactic AI generated adjustments. So first, a very important question. We said we couldn't train a machine learning model to tell apart real corners versus tactic AI adjustments. Can humans tell tactic AI adjustments apart from corners? No, they can't. So here on the right-hand side, you see the average realism scores assigned to real and generated corners. And you can see they're basically the same distribution. And these adjustments are indistinguishable with a p bigger than 5%. So basically, as far as realism is concerned, tactic AI adjustments are indistinguishable from real corners. So that's a good first start. Then secondly, to validate how good our predictive metrics were, we asked our various human raters to predict, with top 3 accuracy, who is the likely receiver of a particular corner. And what we found quite satisfying was that humans on average had a top 3 accuracy of about 79%. And this is a percentage that, if you remember a few slides ago, is comparable with tactic AI's percentage. And what's also very important is that there's no significant difference in the accuracy of predicting who's the receiver of a real corner versus predicting who's the receiver of a tactic AI generated corner, where obviously you don't have ground truth labels, but they come from tactic AI. But the fact that the agreement still stays roughly indistinguishable from the real corners shows that, once again, the predictions coming out of our predictive model are well aligned with human intuitions. So, as a one-sentence summary of these 2 results, experts cannot distinguish tactic AI adjustments from real corners, and experts predict corner kick receivers equally well as tactic AI. These are not necessarily the main questions we want answered, but they're important starting points, right? If tactic AI produces obviously fake corners, then that's not necessarily a tactic you can use in the real world. Next up, because tactic AI has to build these player representations that can help them answer all sorts of questions about the corner kick situation, like who's the receiver or whether a shot is taken, arguably tactic AI has to build up an interesting embedding space representation of players. And therefore, you would expect that tactic AI's player embedding space, here visualized using t-SNE, can result in some very interesting structure assigned to various corners. So we're going to study a couple of situations in this t-SNE space. You can already see them highlighted with yellow circles. I will now gradually expand those yellow circles into various corner kick situations. So one thing you might expect, and it definitely does happen, we've observed it in many cases, is that corner kicks that are structurally very similar tend to receive very similar embeddings from tactic AI. So here, for example, you can see 2 corners that are very close in the latent space of tactic AI, and you can already see the 3 motifs highlighted in purple and white showing that actually structurally these two corners are very similar and they seem like very similar strategies. And you can also see that the swing type is the same in both corners. So the strategy for where the ball is being sent is also the same. And also, as you would usefully expect, if you have corners that are embedded far apart in the embedding space, they tend to have dissimilar motifs. And in this particular case, these two corners that are on the opposite ends of the spectrum, they will correspond to an in-swing and an out-swing corner, respectively. And those two corners are generally quite different situations from a tactical analysis perspective. So these kinds of isolated qualitative observations lead us to believe that tactic AI could be quite useful as a retrieval system. And this is another task that human assistant coaches have to do on a regular basis. Whenever you are playing against a new team, you might find it very useful to analyze what kind of corner strategies they've been having over the past games. So retrieval of similar situations to any particular situation is potentially a very valuable tool for learning more about strategies to employ against this team and anticipate what kind of tactics they will have. So we wanted to validate how well could tactic AI embeddings be used for retrieval. Now, this is not a scenario where you can do a very comprehensive study because there's many different ways in which you can do retrieval. But we wanted to see, just as a simple first sanity check, can tactic AI help us retrieve corners in a more interesting way than if we just looked at raw player positions, which is what a more simple heuristic could do. So we built a simple heuristic using raw feature similarity. So we compared two situations by how close they are in the player coordinate space, and we retrieve a corner which is closest in terms of player coordinates. And this kind of retrieval has been seen as useful by human experts about 33% of the time. So for 33% of the situations, choosing the closest corner to any given corner in terms of input player coordinates gives you a usefully similar retrieved corner about 33% of the time. If instead you choose to retrieve a similar corner based on how similar their tactic AI player embeddings are, you suddenly get a success rate of about 63%, which is obviously quite a significant improvement compared to this raw feature baseline. And what's also encouraging about it is that all of this, to make the case study more scalable, is done in the k=1 regime. So we're only retrieving one similar corner, whereas in reality, an analyst may retrieve 5 or 10 similar corners, which obviously will amplify this probability that you will find something useful within them. So if you look at the specific ratings assigned to whether or not the retrieval is useful, the ones assigned to tactic AI retrievals are significantly higher than when you're using raw features, and this is statistically significant. And also, it's not just that on average, tactic AI embeddings are more useful. Our 5 raters are highly in agreement on which corners are useful and which corners are not useful. So all 5 of them find tactic AI to be significantly better than raw features, and the level of inter-rater agreement is pretty high. So in summary, for the retrieval study, experts prefer tactic AI-based retrievals to retrievals based on directly looking at the raw player features. And experts have a high degree of agreement over this rating. So it's not just that on average they find it better. Every single one of them seems to be in general high agreement over which features are salient and which ones are not. And now we come to the main question, right? We mentioned that we can use tactic AI as a predictive model. We mentioned you can use tactic AI as a retrieval model. But really, the most interesting thing tactic AI can do is do the guided generation. So suggest different tactics or suggest modifications to what different players could be doing in a certain corner kick situation to hopefully increase or decrease shot probability or probability of any particular event. So we set up a comparative study where we showed our expert raters 2 corners. One of them is the adjustment of another, and we assign a rating of +1 if tactic AI improves the situation, -1 if it makes the situation worse, and 0 if there's no difference. So this gives us a score in the range of +1 to -1. And first really exciting result is that averaged over all the scenarios we showed to our raters, the average rating assigned was 0.7, which is a pretty high rating compared to the width of the range. But maybe an even more tangible result is on how many of the corners we showed was on average, it seemed to be a good suggestion. And that number is 90%. So in 90% of all of the situations we showed to our human experts, they, by consensus, agreed that the suggestions from Tactic AI were useful. And once again, just like for the retrieval case, this is not just like an average of some raters being very happy with Tactic AI and some raters maybe being a bit less happy. The inter-rater agreement is very high, which means that the human experts largely agreed on where the suggestions were salient and where they were not. So this is arguably the most important quantitative result of our work. We have seen that the system can be directly useful because experts prefer Tactic AI suggestions over real tactics 90% of the time. And we've seen before they cannot tell them apart from real situations, which is also really important. So these are important suggestions, and they're ones that feel realistic. And once again, experts are not, this is not just on average, experts have a high degree of agreement over the ratings that they have assigned. And while looking at all these numbers is probably very interesting to evaluate how well the model is behaving in the aggregate, I feel like there's always an exciting aspect of analyzing model outputs directly. So I want to show you here 4 specific situations where Tactic AI made suggestions where most or all of our 5 raters thought, yeah, these players are really importantly modified. So here, on the left-hand side, you have a reference corner that happened in an actual Premier League match. And on the right-hand side, you have suggestions by Tactic AI on the defensive team, such that the probability of scoring for the attacking team is reduced. And all the players that have a circle around them are players where our expert coaches have thought that this was an important adjustment. And the brighter the yellow circle, the more experts have said that this is important. And this is a very interesting case because actually all of the defending players, except for one, have been seen as salient suggestions here. And you can generally see that they are being a lot more active. They're positioned better. The goalkeeper is moved further back, which is less risky. And the runs that the defending players are making are far more closely tracking some of the attackers than before. This is a pretty important thing to note because the system was never explicitly trained to do these kinds of heuristics. It has learned them completely by itself by learning how to predict which features are associated with shots and which features are associated with receivers, and then optimizing the predicted positions such that this prediction is optimized in one or the other direction. Here is another interesting example. Once again, a lot of the players on the defending team have seen salient suggestions, and you can generally see, especially in the cluster of the defending players that are closer to the edge of the box, there's now a lot more dynamic movement, which tries to close up the movements of the various attacking players in a way that hopefully will stop the threat a lot more effectively than the more stationary approach from the reference corner does. Here is another situation where you can focus now on the 4 players in the center of the box. Once again, in the first case, they all sort of ran off in a potentially incorrect direction, which doesn't really seek to block anyone. Whereas in the refinement, they are now tracking their runners a lot better and covering a lot more ground more effectively. And the 4th situation, which is maybe an example of a less global but more targeted suggestion that Tactic AI gave. I think we can put most of our attention on the 2 central defending players, which previously were making relatively weak runs, which did not have a chance of strongly blocking the attackers. And those were both now modified to include more proper tracking and covering runs of the corresponding attackers, and these two have been seen as very salient by the expert raters. So this was the last slide I wanted to show you. Let's talk about some conclusions now that we've covered all of this. In our work, we studied a dynamic set of problems, all roughly revolving around inferring corner kick dynamics. And our method was powered by graph neural networks and geometric deep learning. As a result, it meant we had increased data efficiency, and we were able to cope with the challenging data availability constraints in association football. And our model is both predictive and generative. So we can predict whether or not there will be a particular outcome in a football match, like a shot or a receiver event. But we can also have a generative model that can predict how should the players have been positioned to increase or decrease shot probabilities. And the adjustments produced are both realistic and quantifiable. And what's more important is that they're also deemed on average and in terms of agreement significantly useful by Liverpool Football Club experts, and in a domain of corner kicks where you can actually make actionable decisions based on the outputs of this model in a relatively clear way. So in short, as we set out to build an AI assistant for football tactics, we believe we now indeed have an AI assistant for football tactics in our hands. Hope you've enjoyed it. Thank you very much for listening. And I will obviously be happy to take any questions you might have. I'd like to thank once again all of the great collaborators that worked with us on this, both within Google DeepMind and within Liverpool Football Club. And yeah, I remain available for any other points of discussion you have, either during the Q&A session or afterwards. If you want to reach out, I have my email contact and my social networks on this slide. Lastly, I would like to thank Łukasz for inviting me to speak to you all today. This is actually the first time I'm presenting this line of work externally. So yeah, really keen to hear more about your feedback. Thank you very much.
Thanks a lot, Petar. It's great to have this presentation here first. And we do have a couple of questions. However, I wanted to ask first to make it more general. So in the end, what you are looking for is a recommendation system that was validated with, how to say it, with answers from the team from Liverpool Football Club. Is that correct? Like the whole, to make it, to name it.
Right. So, I mean, I guess the result we are most excited about are recommendations in terms of suggested adjustments to player positions and velocities and things like that. But it turns out in order to build a good generative system like that, you also need to have a system that really understands the game. So I believe all of the artifacts we developed along the way, like predictors of receiver probabilities or predictors of shot probabilities, or even these side artifacts like retrieval systems based on the embeddings, are all bound to be very useful. But we basically focus, the main output we were really hoping would work out well was the generative suggestions, and indeed we were quite happy with the qualitative results we received.
So you've had in mind when approaching this problem, you've had in mind the full architecture of the solution, or did you approach it incrementally and an idea came up somewhere in the end that there might be a useful input from one part of the works to be used for another one?
I would say yes and no on this question, because first of all, we sort of knew what the good architecture over the tracking data would look like because we had the graph imputer model I showed you before. So we already sort of knew in the team how to build a model that understands tracking data and player nodes reasonably well. But I would say that there was still an element of being incremental about it, because especially in corner situations, there were lots of these pitch symmetries that we could exploit. So the idea to attach geometric deep learning on top of the graph neural network only came later during the development of the model. So yeah, basically, maybe we knew which tasks we wanted to predict prior to starting the project, and we knew it should be some kind of a graph machine learning model. But the full architecture was something we developed step by step.
All right, thank you. Let's ask the questions from the audience, because there are some. So first is what makes AI in this aspect better than, say, an assistant coach with experience what I believe is how can you go beyond what human is capable in terms of assisting.
Right. So looking at the timestamp, this is a great question. But looking at the timestamp, I think this question was asked somewhat earlier in the talk before I introduced Graph Imputer and all of those different approaches. So hopefully by now it's a bit clearer what kinds of tasks AI is able to zone in on that a human assistant coach with experience cannot. But I will elaborate on it again because I think it's a useful question to ponder. Basically, I would not deny that an assistant coach, if they're really focused on a particular situation, would probably be able to detect a lot of the things that Tactic AI is able to detect. That being said, it does require some effort to spot the right patterns, especially in a sea of 22 players that are sometimes really close to each other, and figuring out really what are the salient collections of players. And also, so not only is it tricky to spot, you might miss something if you overfixate on a particular motif that you're very familiar with. And I think one thing Tactic AI can help you with is basically pretty much immediately output to you, hey, these parts of the corner are looking interesting. These players might be a bit falling asleep on the job, or you might need to adjust their position a little bit. So these kinds of immediate feedbacks can basically help accelerate the rate at which the human experts are able to do their job and analyze more situations, and maybe even detect novel variations that they might not immediately think of because they're not explicitly familiar with them. So I would say it doesn't necessarily, and to be honest with you, this is really the most exciting kinds of AI applications, in my opinion. Like, they don't necessarily invent this brand new skill that the AI assistant, that the human assistant coach didn't already have, but they allow them to do their job much more efficiently and basically come up with more, leave more time for creativity and less time for like mundane pattern hunting.
Yeah, sure. For the new features to be probably very difficult to be validated if it would came beyond what human do. Actually, I feel. All right. Then next question is: can it be implemented in the real time or only retrospectively? As you said, it was difficult to make it online system.
Yeah. So I think you can implement a system like this in real time. Like, I think speed-wise, it's not really a big problem. But what I would say, though, is that like my claim was more that you don't really want to do decision making in real time, because the players will easily get confused if you shout instructions at them in the middle of the game. I think like you really need to focus on what's happening, right? So corners are a really good candidate here, because actually the corner kick strategies are decided before a game even begins, right? So you can actually influence that strategy building aspect before the game even takes place by using the kinds of analysis that Tactic AI offers. So to answer this question, I think you could implement something like this in real time and maybe even make some kind of immediate adjustments. Maybe you can, well, one thing you could do, I guess, is substitutions. Like, you could decide to substitute certain players in if you see that they would be giving you a much higher shot probability in certain scenarios or something like this. Or if they are, less fatigued than other players and so on. But I would argue most of the salient decisions still should not happen in real time, I would say, because you have a risk of introducing confusion if you do this.
Yeah. Another one is comment. I read your paper, amazing work. Thank you. However, I'm a little confused as to why you only consider the position, height, and weight in your work for describing a player's skill in aerial duels.
Yeah, this is an excellent question. I see it's a multiple part question, so thanks, Andrei, for asking this. I would say, maybe I should have more explicitly said it, we deliberately focus on a very minimal set of features just to show you, with some data that can be readily available to most football clubs, you can make a difference already and make salient suggestions. In reality, a lot of these things become more nuanced when you introduce various player profiles. For example, as mentioned, skill rating systems on aerial duel skills and things like that, which, as you go deeper into the specifics of features, you go deeper into, what each individual club is computing and capable of inferring based on the data available to them. So, this now falls into the realm of what individual clubs might do with this kind of data. we really deliberately focused on data that's fairly generic, just to show that the idea works, even if you take away a lot of that nuance. But of course, I would expect the model to perform a lot better if it has access to these kinds of additional features, right? Note another thing that we're not using at all is where the ball is and which direction the ball is moving. All we know is at the moment the corner is taken, where each player is and which direction they're going in. That's all our model knows. So with more data, you can have more accurate models as well, of course.
Right. And another follow-up one is that we could calculate the win percentage in the previous matches, which might help to simulate corners more accurately.
Yeah, so this is basically what I saw, that all these questions came from the same person.
Right.
And I tried to capture my answer to all of them in the same one.
All right. So if you have any more questions, just talking to the audience, feel free to ask them. One thing I was curious about, because the Tactic AI module is outputting the embeddings to the Disney itself, or do you call Tactic AI like the whole system? I was lost a bit into this one.
So the Disney thing is really just to make it prettier to look at and actually make sense of the space. In reality, it's a higher dimensional space which we cannot visualize, right? Really, like, the Disney is there for us to just have visual inspections, and the retrieval takes place over a much higher dimensional space that we cannot easily plot on a slide. That being said, a Disney could still be useful if you want to design like a tool where a human can like explore the latent space of corners and like look at similar corners by clicking on them. But I would argue, because you're doing a dimensionality reduction by doing a Disney, you are effectively destroying some of the useful structure that the Tactic AI has learned by doing that. So yeah, I would probably, I wouldn't use Disney as the actual vector used to mine similar corners, but it can be a really cool visualization technique. And so for us, the Disney analysis was really just to see that we believe there's something useful happening in this latent space, and we have some qualitative evidence for that. And that then motivated us to do the case study with humans.
Yeah, I thought maybe that was used for the ranking, like you had it clustered, and then you knew that there is some part of candidates that you could use the answers from as a result. But as you said, it's only for the visual aspects.
Yeah, it's more blind than that. Just take the closest one in the embedding space, and we're not really trying to hunt for clusters at this point.
All right, and there is one more question. Does the system change according to the team, or does that not make a difference?
So, okay, currently the model does not have information over the identities of the teams, which obviously would help. It doesn't have access to the current score or the weather or these kinds of features that can all influence like what kinds of strategies or success rates you could have. Once again, this all falls into the realm of additional features you could introduce into the model. Obviously, in some sense, the system will change according to the team, just because the player vectors are going to be different for the two teams, right? So in that sense, when you put a different team into Tactic AI or you substitute certain players, you will get different outputs, right? But there's no explicit team identifiers in the prediction. No.
All right, thank you. And maybe last question, because we're running out of time. I was curious about when you're using the graph neural network for this kind of task, do you somehow make a different iterative approach to rewiring that input graph so that you can see the difference in between each, let's say, recommendation and suggestion?
Right. So we do not do this in this particular paper, mainly because in football, the number of nodes is not that big, right? It's 22. So it's like there's whenever a graph is that small, and when you don't have to generalize to bigger graphs, that's also an important aspect. My general heuristic is that fully connected graphs tend to be a pretty good idea. And it's really hard to come up with rigid sparse graphs that will do a better job. That being said, if you read through our paper, I obviously didn't have enough time to cover all those in-depth details, but our main architecture is a graph attention network, meaning that we do have an attention mechanism over the edges. And while we don't have these results in the paper, we have like informally analyzed what are the graph structures that this model kind of learns to build. And there is some loose correspondence between how strong attention coefficients you compute and like player synergies, as sort of loosely estimated by how much do these two players like to pass with each other and things like that, although we never explicitly put this feature in the model. And when we showed this to folks from Liverpool, I think they were interested in the correlations coming out of the system, but we were not completely convinced how we can kind of usefully make advantage of such a system to drive decision making. So basically, it was deprioritized compared to everything else I showed you today. But yeah, I think from the perspective of like looking at attention coefficients, there's definitely some interesting rewiring happening implicitly inside the system.
All right, my last question. Who can use tactical AI? Is it for the Liverpool? I'm not sure if it's confidential or not, but...
I think we mentioned this in our paper's method section. The base models that Tactic AI uses are models from DeepMind's GitHub repository of CLRS30, which is publicly available. So the exact model that we use, minus the geometric deep learning part, which I think you can easily slap on top of it, is already publicly available, and there is open source code. The data, the data is something that depends on what you're able to get. I do believe there exists some open repositories of football data you can play with. The specific data we have used was proprietary, but that doesn't mean that if you have access to a particular data set you want to deploy it on, you wouldn't be able to do that. So I would say Tactic AI, the model, can be used by anyone, and large parts of it are effectively already open source. But finding good data to put into Tactic AI, that depends on who you are and what kind of data you would like to play with. So,
yeah, sure. Thanks again, Petar, for all the answers, the presentation itself, and for accepting the invitation. It was a pleasure for us to have you today. And any closing thoughts from your side?
Well, thanks again for inviting me for this event, Łukasz. It was a nice and dynamic opportunity to present our work. I also really enjoyed the interactions with everybody who asked questions. And I hope to have a chance to present to you all again once we have some other new significant result come out in the future. So thanks again for the opportunity.
Sure thing. Thank you. So thanks to all who asked questions as well. I really appreciate it. And once again, Petar, thank you. And